are parallel lines, but there is one unique parallel line through any point you care to name. Single unique parallel line. That's important for later. Going back to our spherical geometry, well, the fourth postulate is fine. Right angles are still right angles, at least as far as we can tell. But the first and second postulates, they're a little shaky. There's a lot of shortest lines between the North and South Pole, none of them unique, and there's an infinite number of them, and we call them the lines of longitude. For the second postulate, yeah, you can keep extending a line on a sphere, but it wraps around on itself eventually, so is that really infinite? It's kind of shaky. The third and fifth postulates, though, they're kind of completely broken. You can't draw a circle of any radius on the sphere because there's a maximum size to the sphere. And the fifth postulate is in shambles. You can start out with two lines that seem parallel, but as you extend them, they eventually intersect each other. Think of the lines of longitude again. They intersect at the poles, even though they start out parallel at the equator, or at least they start out looking parallel at the equator. We've already seen that triangles get beefy on our sphere. They have more than 180 degrees. But we also lose several nice things from Euclidean geometry. I'm just going to run through them real quickly. If we try to draw similar triangles, triangles that have the same angles and different side lengths, turns out we can't. The only way to get a triangle with the same angles on our sphere is to draw a triangle with the same side lengths, exactly the same side lengths. This also means that the Pythagorean theorem no longer works. There is a lot more that can be said here. For example, we could get our third postulate back by using a curved infinite plane instead of a sphere. This is called elliptic geometry, and it will come back later. But I think we can already see that our experiment with spheres and triangles has brought up some really surprising results already. To wrap this section up, when we examine a new interesting idea, it helps to compare it with old ideas, not just to find the differences, but the similarities as well. In our example, we could still draw straight lines and points and triangles, but the way those things worked and the way they interacted with each other changed on the new setting. As I've said, there's a lot more we could learn from spherical geometry, but we already have some interesting and surprising experimental results here. With these results in hand, we can move forward to the most important and scariest part of the whole process: checking our work and then showing it to others. In short, peer review. Part 3. How does our work hold up to peer review? Well, one way we could figure out if our results are convincing to other people is to simply say, our results make sense, we don't need to convince you, hooray. But if you actually want to work towards being convincing, you need to put in a little more legwork. Of course, what's going to be convincing depends on your audience. If you're just teaching a 5th grade math class about 180-degree triangles, they're not going to need that much convincing, but they may not understand what you're saying without more help. On the other hand, your peers in the math department will probably need a lot more convincing. So much so that they need heavy attention to detail and logic, what we call rigor. Now, the process of how to rigorously prove a theorem could be the subject of an entire video series, so instead, I'll focus on two really broad categories of, now I'm going to show my community this cool thing I made. Number 1, critique, checking if your mathematics is built on relatively solid logic. And number 2, continuation, adding to the idea with further investigations and experiments, bringing the idea into new contexts, comparing the new idea with old ideas, or directly combining the idea with other ideas. There's a lot of ways you could categorize peer review. This is just a simple one for the purposes of this video, and I think it'll be fine for now. Since I'm not going to be looking in depth into the incredibly important section of mathematics that is making your arguments rigorous, let's instead take a step back. In our real-life history, we know that non-Euclidean geometry has been a thing that we've been studying for hundreds of years. So why don't we look at the historical process of peer review for our non-Euclidean geometry? Part 1, the critique. To begin with, most people didn't focus on spherical geometry for its own sake. What these mathematicians, including Alhazen of the Islamic world and Saccheri of Italy, what they're trying to do instead of focusing on spherical geometry was more about investigating Euclidean geometry. They were looking at that complex fifth postulate again, and they were trying to prove maybe that it's not its own axiom, but it was a theorem that could be proved from other axioms. So they were using spherical geometry as a test case for, if we break the fifth postulate here, where there are no parallel lines at all, can we prove that the great geometry of Euclid is the most correct of them all? In short, they went in with a bias. To be fair to them, though, spherical geometry just kind of breaks too many of Euclid's postulates. Like I mentioned in the last section, our third and fifth postulates are broken outright, and our first and second are on shaky ground. To finally convince the mathematics community that you could have valid non-Euclidean geometry, we needed not just spherical geometry, but other kinds of geometry on firmer ground. This process took several hundred years of back and forth, and I cannot cover it all here. But I want to highlight one of the steps toward a fully convincing argument. Eugenio Beltrami's proof that hyperbolic geometry is just as consistent as Euclidean geometry is, and vice versa. What is hyperbolic geometry, though? Well, to oversimplify a lot, instead of your beefy triangles from spherical and elliptic geometry, hyperbolic geometry has triangles with less than 180 degrees, skinny triangles. It also has infinite parallel lines instead of 0 or just 1. Another weird quirk of hyperbolic geometry is that if you look at the infinite hyperbolic plane, it's weird in that you cannot actually fully visualize it in 3 dimensions. You have to be in 4 dimensions to do that. There's tricks you can do to sort of squash it down to 3 dimensions or 2 dimensions, as you can see on the slide here. But it's weird that you have a good example of elliptic and spherical geometry with a sphere, but not really with hyperbolic geometry. Anyway, the fact that Beltrami could prove that hyperbolic geometry and its axioms were at least as consistent as Euclidean geometry. If something was wrong with hyperbolic geometry and eventually the other non-Euclidean geometries, then there was something equally as wrong with Euclidean geometry. There was no supremacy of Euclid. And one of the things that implied was that people had assumed before that our universe was just Euclidean. But with non-Euclidean geometries in the race now, whether or not the universe is Euclidean or not has to be proved through observation and experiment by astronomers and cosmologists, not by mathematics alone, as people had assumed for hundreds of years before, which was ludicrous to them. The other part of peer review is continuation. There's a lot of great things that came out of non-Euclidean geometry in the years that followed it, and a lot of work it inspired. But I'll focus on one application here, general relativity. One of the main players in the formulation of non-Euclidean geometry was Bernhard Riemann, of Riemann hypothesis fame. He first formulated elliptic geometry, but he also described the more general Riemannian geometry. The thing about elliptic geometry and spherical geometry is that you have positive curvature,